Hello everyone, this is lecture 4 of ComSci 142, Sorting Algorithms. In this video, we are going to discuss 10 different sorting algorithms. So let's start with the sorting problem. In the sorting problem, we are given an array of items as input, and for the output, we will give the sorted version of the array. So we're supposed to arrange the items according to an order. It could be ascending order or descending order depending on the problem. The sorting problem is the most ubiquitous combinatorial problem, so it can be found everywhere. That's why it's very important in computer science because a lot of algorithms build around it. So if you remember from our previous video in search algorithms, a couple of those search algorithms assumed that the input array was pre-sorted. So you would need a sorting algorithm to do that. Okay, so examples of those were binary search and the jump search, which needed your input array to be already sorted. Okay, now there are two types of sorting algorithms. So it could be a stable sorting algorithm or an unstable sorting algorithm. So how do we distinguish the two? In stable sorting, if there are two items with equal rank, they should appear in the same order in the sorted output as they appeared in the unsorted input. Okay, what does this mean? So let's see an example. Let's say that our input is 5, 1, 2, 1, 3, 4. Now we have two 1s in the input. So let's name this 1A and 1B, just to distinguish between the two. If it was a stable sorting algorithm, the result should be something like this, right? 1, 1, 2, 3, 4, 5. But if it's stable, 1A should be the first one here, and 1B should be the second one here, because that is the order that they appeared in the input. Okay? So, if they are tied, they should appear the same way as they did in the input. Okay? That is stable sorting. Otherwise, if it's something like this, 1B, 1A, 2, 3, 4, 5, then we call this an unstable sorting algorithm because the order changed from the input to the output, even if they are tied, basically in the ranking. Okay, so that is stable versus unstable sorting algorithms. Now, another distinction that we could make is between out-of-place sorting and in-place sorting. So if you have an out-of-place sorting algorithm, that means that it uses an extra data structure in sorting. So it could use an extra array or extra queue or deck or other data structures in doing the sorting. But if it's in place, then we are sorting on the input array itself by doing swaps. Okay? So we don't need extra memory, we don't need an extra data structure if it's only in place. Okay? So later on, when we talk about the sorting algorithm's memory consumption, we are talking about the extra memory needed by the algorithm. So extra data structures or extra arrays. Okay? It doesn't include the input array because that's already assumed to be part of the problem. Okay? So we will only analyze the extra memory needed by the algorithm. Okay? So let's now start with our first sorting algorithm, which is selection sort. Okay, now selection sort is a naive sorting algorithm. It's very simple, and it's also one of the slowest because it's fairly simple, right? So it repeatedly performs the same task without learning from previous iterations. Okay, so that's why it's naive. So how does selection sort work? So basically, how it works is like this. First, you need to find the first smallest element, and then you swap it with the element in the first position because that's the smallest one. And then you do that. You do the same thing for the second smallest element and swap it with the second position. Find the third smallest element and swap it with the third position, and so on until you have found everything. Okay? So the selection sort actually minimizes the number of swaps because at most you'll be doing n swaps if n is the number of items in the array. Okay, because later on, in other sorting algorithms, we'll find out that other algorithms do a lot of swaps. Okay, like for example, bubble sort or insertion sort, they would do more than n swaps. Okay, so selection sort is useful when swapping in memory is costly. Okay, so because it minimizes the number of swaps. Okay, so this is the pseudocode for selection sort. Okay, so given an input array A, and assuming that array A has n items, so we'll go through the loop for I from 1 to n. So let x be the ith smallest element and swap x with the item at index I. Okay, so let's see an example of that one. So if our input array consists of 5, 3, 1, 2, and 4, so what we'll do is first we'll need to find the first smallest element, and that would be 1, right? So we'll swap 1 with the first item in the array, which is 5. So that would be 1, 3, 5, 2, 4. So we basically swap these two. And now this part here is already sorted. So we'll continue with the rest, which is this one. Now, what is the second smallest element? And we'll find that it is 2. And then we'll swap that with the second item in the array. So they will be swapped. So that would be 2, 5, 3, 4. And then after that, the first two are now already sorted. So we'll continue with the rest. And then the third smallest element out of this 3 would be this one. So that would be 3. And we'll swap that with the third element. So they'll be swapped. So that would be 1, 2, 3, 5, and then 4. And now the first 3 items are sorted. And then we'll continue with this. So the fourth smallest element is 4. We'll swap these 2. And then that would be 1, 2, 3, 4, 5. So the first 4 elements are sorted. But when we go to the last one, it's the only element left. So that's also sorted by itself. So everything is now sorted. 1, 2, 3, 4, 5. Okay? So that is selection sort. Okay? Pick the ith smallest element, swap it with the ith item in the index, and then do it n times, basically. Okay? So that is selection sort. Okay. Now, if we have a more detailed pseudocode for the selection sort, we have the following. So for I from 1 to n, the ith smallest is currently a sub I. Okay, and then this loop will try to find the ith smallest element from the rest of the array. So from I plus 1 to n all the way to the n. Okay, and then when you find the smallest, so you keep updating it if it's smaller, right? You swap it with the a sub I. Okay, so why are we looking at a more detailed version of the pseudocode? It's because we're supposed to analyze the algorithm for its running time. Okay, so the outer for loop, this one, will run n times because it's from 1 to n, right? So that's n times. But the inner for loop here, it depends on the iteration, okay? Because it's from I plus 1 to n, and I varies per iteration. So let's say that we have n is equal to, let's say, 4. So that would be from, if I is equal to 1, 2, 3, and 4. So what would be the range for k? K would range from 2 to 4. This one would be 3 to 4, and then 4 to 4, and then here wala na siya because it's already the last item in the array. Now, how many iterations would that be? So 2 to 4, that would be 2, 3, 4. So there's 3 iterations, 2 iterations, and then 1 iteration, and 0. So in total, if we add all of that together, that would be 1 plus 2 plus 3, right? Or, in general, that would be 1 plus 2 plus dot 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 all the way up to n minus 1, where n was 4 here, and then we only added up to n minus 1. So this is the general form. And if you remember, the form for adding like 1 plus 2 up to n, this was equal to n plus 1 over 2, right? Which is about O of n squared. Okay? So that is the analysis of the running time of selection sort. Okay? So, the best case, worst case, and average case are all O of n squared. Again, because okay, so earlier we saw that for n is equal to 4, 1, 2, 3, 4, the number of iterations here were 3, 2, 1, 0. And so if we added all of that, that would be 1 plus 2 plus 3, which is equal to, in general, 1 plus 2 plus dot 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 n minus 1. Okay, and this is about n squared. And it's the same whether it's the best case if it's already sorted. The worst case is if it's reverse sorted. And average case, which is, let's say, random. Because, regardless if it's sorted or not, or randomized, we'll still do the same thing anyway, right? We'll pick the first smallest element. So let's say it was already like this, 1, 2, 3, 4. So we'll still pick the first element, swap it with this one. Pick the second element from here, swap it with this one. Pick the third smallest element, swap it with this one, and pick the fourth smallest element and stay there. So it's still n squared ang running time niya. Okay? And then the memory is O of 1 because there's no extra memory needed. Okay? So that is selection sort. It's very naive. Okay. So let's now go to the second one, which is insertion sort. And from the name itself, the idea is to insert the item into the correct position. Okay? So the analogy here is, so remember when you're playing cards, so you get the hand of cards that you have, and then of course as you get them, they're still in random order like this, right? And when you want to organize your cards, you might do something like, let's say, so 10 would probably be somewhere here, right? And then 8 would probably be somewhere here. Okay, so you're inserting the cards into their correct position. So then that would become 6, 8, 9, 10, queen, something like that. Okay, so if you insert 10 after 9, and then 8 before, or 8 after 6, so this would be the correct order. Okay, so that's the basic idea for insertion sort. And insertion sort is an in-place sorting algorithm, meaning it doesn't use extra memory. And in doing insertion sort, the array is actually sorted incrementally. So you are increasing the sortedness of the array as you go. Okay, and it's efficient for small arrays and nearly sorted arrays. If it's already close to the sorted version, then it's a good algorithm for that one. Okay, so this is the pseudocode for insertion sort. So for again, given an array A, for I from 1 to n, we will think of the items before A sub I as the sorted items already. Okay, and then we'll shift items that are higher than A sub I in the sorted items one place to the right, and insert A sub I to its correct position in sorted items. So basically, we will insert A sub I to the correct position while shifting others that are higher than it to the right. So to make room for the the inserted item. So this is an example of insertion sort in action. So let's say this is our input array 4, 3, 2, 10, 12, 1, 5, 6. Okay, so of course, if we start with 4 by itself, then that's already sorted. So this part here is already sorted. Now the next one that we'll look at is 3. Okay, so now 3, where should 3 go? So we'll compare it with 4. Now if it's less than 4, so we should insert it before this number 4. Okay, and so when we swapped it out here, this part is already sorted. Okay, 3, 4. Then the next one is 2. Okay, so for 2, where should we insert it? Should we insert it 4? It's less than, so we could keep going. So is it less than 3? Yes, so we could keep going, and then we'll insert it here. So we insert it here, and then this part is already sorted. Okay, now for 10, when we compare it with 4, it's already greater than 4, so we don't need to swap anymore. So this part is already sorted. 2, 3, 4, 10. Now next, see 12 is the same. So when we compare it with 10, here, it's already greater than 10, so we know that we don't need to insert it into the correct position. It's already sorted at this point here. Now how about 1? So we'll have to compare it with everything here, because 1 is less than 12, is less than 10, less than 4, less than 3, less than 2, and so the correct position is somewhere here. Okay, so we have to swap or insert 1 all the way up to the front and move all items forward. So we know that everything up until here is already sorted. Okay, and then last 2 na lang. 5, where should it be inserted? So is it less than 12? Yes. Less than 10? Yes. Is it less than 4? No. So we'll stop here. Okay, and we know that the correct position to insert 5 is after 4, which is here. So we'll swap 5 here and then move 2 items forward. So we know that everything is sorted up until here. And then for 6, we'll do the same. So less than 12, yes. Less than 10, yes. Is it less than 5? No. So we'll go back and insert it here. And when we insert 6 here, then everything is already sorted. Okay, so this is what we mean by increased sortedness, because from the first iteration, so the first one is sorted, the second up to the second, up to the third, and so on until everything is sorted already. Okay, so that is insertion sort. Okay, so a more detailed version of the insertion sort pseudocode is given here. So for I from 1 to n, your current item is the a sub I, and then you go to the left, okay, because you're assuming again that everything before a sub I is already sorted. So start sa left, I minus 1, and until left is still greater than 0, meaning you haven't fallen off the left edge of the array, and left is still greater than the item, so meaning you could still move the item to the left. Keep going, okay, until you find the correct position to insert it into. And when you've done that, insert it into the correct position, and you have already shifted the other items to the right. Okay, so for the analysis, the outer for loop still runs n times, because again you're going from I from 1 to n, okay, assuming n is the number of items in the array A. Okay, the other loop, the while loop, actually depends on the input structure, because we don't know how many times it would traverse to the left, because if it's already sorted like this, like for example if you're currently at 3, when you ask it here, it will only ask once because it's already sorted. So for example, if you ask 4, if you ask 3, it's already greater than 3, so you will immediately stop. right? But if it's like, say, like this, for example, let's say, no. So let's not do that one. Maybe if it's something like this, like 2, 3, 4, 5, 1. So let's say that we're already done with this one, and then we're left with this one. So it could be here, no, here, no, here. It could go all the way up to the end if it's 1. But what if it was, let's say, another 3? If it's 3, it will only stop until here, right? So we really don't know how many iterations this while loop could go on for. So it depends on the input structure, meaning is it sorted or not sorted or random. Okay, so how will we analyze this one? So in the best case, it would be O of n, because the best case is if it's already sorted. So if it's already sorted, it would look like this, right? So there are n iterations in the outer for loop, and in each iteration, you only need to ask once, because when you look to the left, it's already bigger than the ones to the left, so it will immediately stop. So that's why if it's only one iteration or one step per iteration, it would be O of n in total, right? If it's nearly sorted, it's almost the same. So you could have like 1 or 2 steps that would also be around constant, so that would still be around O of n. Now the worst case and average case would be around n squared, because what would be the worst case if it's like if it's reverse sorted, right? So 5, 4, 3, 2, 1. So for 5, for example, so assuming that this is the only one for now. So if we look at 4, we'll have to insert it here. So it becomes 4, 5, 3, 2, 1. And then for 3, we'll have to insert it all the way here. So that becomes 3, 4, 5, and then we remove this one. Then for 2, we'll have to insert it all the way up to here. And then for 1, we'll have to insert it all the way up to the front. So that would be around n squared, because for n iterations of the outer for loop, and then for each one, or no, it's similar to the analysis for selection sort. So like if it's I is equal to 1, 2, 3, 4, 5. So this one will have how many? So only have 1 as also, but this one will have 2. This one will have 3, 4, and then 5. So if we add all of that together, this is still the 1 plus 2 all the way up to 5, or 1 plus 2 plus all the way up to n, which is n plus 1 over 2, which is O of n squared. Okay, that's why the worst case is O of n squared. And the same is true for average case, because even if you don't traverse the whole thing, even if it's just half, it's still around n squared. Okay, now for the memory, it's still O of 1, because this is an in-place sorting algorithm. You're not using extra memory. Okay, so that is insertion sort. The next one is bubble sort. And for bubble sort, what we'll do is we'll repeatedly swap adjacent out of order items. So if they are adjacent, meaning they are next to each other, and if they are out of order, meaning they're not in the sorted order, then we will swap them. Okay, and what will happen is small numbers will bubble up the array, meaning they will go to the front. Okay, and we'll also see the same scenario wherein per iteration the first I elements are sorted. Okay, so this is the pseudocode for bubble sort. So do the following while a swap occurred. So for each adjacent pair of items, swap if they are not in order, and do this repeatedly while a swap occurred in the previous iteration. Okay, so that's what we'll do. So let's see an example. So we'll start at the back. Okay, 9 and 1, they are adjacent, right? So are they out of order? Yes, so we'll have to swap them. Okay, so this becomes 1 and then 9, right? And then 4 and 1, these are also adjacent. They're also out of order, so they will have to be swapped. So this becomes 1, 4, right? Then the next adjacent pair would be 8 and 1. They're also out of order because 1 should be here and then 8 should be here. Okay? And then 2 and 1 is also out of order, so we'll swap them. 1 and then this one will become 2. And then 1 and 5 are also out of order, so this becomes 1 and then this becomes 5. Okay? So this is now after the first iteration. So we've seen 1 bubble all the way up to the front. Okay? So it's already here. Okay? Now, since there were a lot of swaps that happened, we'll continue. So how about now? 4 and 9, are they out of order? No, they're actually in order because 4 comes before 9. So we'll leave that as is. 8 and 4. Okay, so 9 is still here. 8 and 4, they will be swapped because they're out of order. So that would be 4 and 8. Right? And then 2 and 4. They will not be swapped because 2 actually comes before 4. So that would be here. But 5 and 2 will be swapped. So 2 would be here. And then 5 should be here. Right? So they would be swapped. And then 1, as we know, is already in its correct position. So now the first 2 items are already correct. Right? And since we did the swap, we'll continue. Okay? 8 and 9, do we swap them? No. 4 and 8, do we swap them? No. 5 and 4, do we swap them? Yes. So that becomes 4, 5, 8, 9. Right? And then the same for 1, 2. So now the first 3 items are already sorted. Now next, let's check. 8 and 9, do we need to swap? No. 5 and 8, do we need to swap? No. Now since there are no swaps that happened, we can already safely assume that everything is already sorted because everything was already in its correct position. So we have already correctly sorted 1, 2, 4, 5, 8, 9. Okay? So that is bubble sort. Look at adjacent items. If they are not in order, swap them and then do the same for the next adjacent item, and so on. And while there was a swap in the previous round, do the same thing starting from the back again. Okay? And then stop only if there are no more swaps that happen. Okay? So that is bubble sort. Okay. Now the more detailed version of the pseudocode for bubble sort is seen here. So you have a flag, a boolean flag swapped, which is equal to false first, and then from n to 1, so you have previous is the current minus 1, and then check if we need to swap them. So if the previous is bigger than the current, so we need to swap them, and then we'll set the swap flag to be true so that we can repeat this one again, and then we'll do that all the way up to 1. So we'll look at adjacent pairs from the back all the way to the front, and then we'll do this while swap is true. Okay, so the for loop here inside is from n to 1, so this takes n iterations, but the outer for loop, the outer do while loop, depends on the input structure. Okay, so we don't know how many rounds it could go on, because if it's already sorted 2, 3, 4, 5, then that means that we'll only need to go 1 round here, because after 1 round we'll find out that there are no swaps that happen, so we'll already be done, right? But if it's, let's say, reverse sorted, that's the worst case, then we'll have to do about n iterations of this. So n iterations times n per iteration, that would be O of n squared at the worst case. Okay, so that is the analysis of bubble sort. Okay, so best case again is O of n, and that is if it's already sorted, because you'll only have to go through one round and find out that there are no swaps needed because it's already sorted. So n adjacent pairs times one round makes it O of n, right? And for the worst case and average case, it would be n squared, because let's say for this one, what will happen is after round 1, this will become, let's say, 1, 2, 1, 3, 1, 4, 1, 5, right? So that there's 1 here, and then after round 2, what will happen is 2 will bubble up here, and then 5, 4, 3. Okay, after the next round, that would be 1, 2, 3, 5, 4. That's third round. And then the next round is 1, 2, 3, 4, 5. It's the fourth round. But since there was still a swap in this round, we'll still have to go another round. And in this round, we'll find out that there are no more swaps. So everything is already done. But how many iterations did we have? So there are 5 iterations also for a 5 item array. So there are n pairs times n rounds, and that makes it O of n squared. Okay, so that is the analysis for bubble sort. And as usual, the memory is still O of 1 because it's an in-place sorting algorithm. We're not using extra memory. Okay, so that's bubble sort. Then the next one is something called the shell sort. Shell sort generalizes exchanging sort algorithms in that it swaps far apart items. So earlier, we saw that for bubble sort, we swapped adjacent items. Now for shell sort, it could do this faster by swapping far apart items. Okay, so it can move out of place items faster than bubble sort. The idea for shell sort is that we'll arrange the array into a 2-dimensional array, and we'll use this concept of gaps. So I'll explain what the gaps are later, but basically, if let's say your gap is 4, then the number of columns in the 2D array would be 4 also. Okay, and then what we'll do is we'll sort the columns of the 2D array, and then we'll after sorting the columns of the 2D array, we'll rearrange it back to the 1D array, and then we'll repeat this time with a smaller gap. So if let's say you used 4 as the initial gap, you could use 2 as the next gap until you have the last gap as 1, and then that's when you sort everything. Okay, and as usual, the sortedness of the array increases per gap. Okay, and it is known to have acceptable running time for even moderately large arrays. Okay, so earlier, insertion sort, bubble sort, selection sort, those only work for small arrays because they are in n squared in a worst case. But for shell sort, it has acceptable running time even for big arrays. Okay, so this is the pseudocode for shell sort. So we'll choose the initial gap, and then while gap is not yet equal to 1, we'll arrange the subarrays per columns, and then we'll sort each subarray, and then after that we'll choose the next gap, which should be smaller, and then repeat everything. Okay, so this would be better explained with an example. So let's say that this is our input array, so 9, 8, 3, 7, 5, 6, 4, 1. So we have 8 items in the array. So we'll use this gap sequence 4, 2, and then 1. So what happens if we have gap is equal to 4? So we'll arrange this in a 2D array with 4 columns. So that would be 9, 8, 3, 7, and then 5, 6, 4, 1. So this is the 2D array with 4 columns. And then what we'll do is we will sort each column separately. So if we sort this column, this becomes 5 and 9. This one becomes 6 and 8. This one becomes remains 3, 4. And then this one becomes 1, 7. Okay. After doing that, this will be our new array now. So that would be 5, 6, 3, 1, 9, 8, 4, 7. Now, what did you notice? The sortedness of the array increased because, for example, 5 here moved all the way to the front, while 9 moved back here, which basically made them closer to their correct positions. Okay. Now, next, we'll use this new array, and then we'll use gap is equal to 2. So now, we'll only have 2 columns. So that we'll have 5, 6, 3, 1, 9, 8, 4, 7. Okay, so this one was used here in gap 2. And then we'll sort each column again. So this becomes, the sorted version is 3, 4, 5, 9, right? And then here it becomes 1, 6, 7, 8. So if we unravel this into a one-dimensional array again, that becomes 3, 1, 4, 6, 5, 7, 9, 8. And you'll notice again the sortedness of the array increased because, let's say, 1 here moved from here to here, closer to its correct position. Okay, and even the 9 here moved all the way back, which is closer again to the correct position. And then finally, we will sort this with gap is equal to 1. So we have 3, 1, 4, 6, 5, 7, 9, 8. And the sorted version of this would be 1, 3, 4, 5, 6, 7, 8, 9. And now, what was the point of doing this per column if we were going to sort it as one column anyway, right? It is now faster to sort with gap equal to 1, meaning everything, because the sortedness of the input array has already increased from here, which is like close to inverse because 9, 8, 7 are in the first parts and 1 is all the way at the back, to something like this, which is closer to the sorted version. So this is already nearly sorted, so it's faster to sort this one than the original array. Okay, so that is shell sort. So now, by the way, the gap sequence that I used here are arbitrary. So you could use your own gap sequence. It could be 5, 3, 1. It could be anything as long as the gap decreases per iteration and eventually leads to gap is equal to 1 as the last one. Okay, so that is shell sort. Now, for the analysis, we can't do a proper analysis of the shell sort because the running time actually heavily depends on the gap sequence that you use. Okay, so if you have a good gap sequence, it could increase the sortedness of the array faster. But if you have like a random bad gap sequence, it might not help as much. Okay, so if you have a different gap sequence, it could lead to different running times, and the running time can also depend on an auxiliary sorting algorithm. So which algorithm are you using to sort the columns? So if you're using, let's say, selection sort as the other sorting algorithm, then it could run slower than maybe if you use something like Quicksort or other faster algorithms. Okay, so some known running times for shell sort could be around omega of n squared, omega of n 3 over 2. So this is n of this is n squared, this is n of 1.5, and then this is n of 1.33, because this is 1 and 1/3, right? So that is better than n squared, because this is 1.5, this is 1.33, but it's still not O of n, right? Because you're still doing repeated iterations, or depending on the gap. Okay, so but at least it's an improvement on bubble sort and insertion sort and even selection sort. Okay, so that is shell sort. Okay, next we have merge sort. You're probably familiar with this one. So it uses the divide and conquer approach, and just a quick background on divide and conquer, although we'll focus more on this in the next set of topics, the next few weeks. But basically, for a divide and conquer algorithm, what you do first is you divide, and what you mean by that is you break the original problem into sub-problems, which are smaller versions of the original problem. And then you conquer each sub-problem by solving them recursively. And then, additionally, there's a merge step where you combine the solutions to the small sub-problems to form the solution to the original bigger problem. Okay? So divide, conquer, and merge. So we'll learn more about this in the next few weeks when we dive deeper into divide and conquer. But for now, let's focus on merge sort. Okay. So for merge sort, what we'll do is first, as long as n is greater than 1, so you could still divide it into 2. Find the middle, which is n over 2. Again, n being the number of items in array A. M is the middle, which is n over 2. And then we'll recursively call merge sort on the first half from 1 up to m. So the 1 up to the middle, so that's the left half. And then call merge sort on the right half, so m plus 1 all the way up to the end, which is n. Okay? And then after doing merge sort on the two sub-problems, we will merge their answers to the original one. Okay? So, for the merge, what will happen is basically you have the left half and the right half. And for I from 1 to n, what we'll do is compare the first elements of each half. And whichever is the smaller component between the two gets copied to the answer first. Okay, so I'll show this later in the example of what we mean by this in merging. But if you want a more detailed pseudocode of the merge, you can find it here. You can also find this in the lecture notes, so you can just study this one. But basically, we're just comparing if which of the two, a sub left or a sub right, is greater, or sorry, smaller. If whichever is smaller gets copied first, and then you move forward to the next one. Okay, so yeah, so let's show an example to make this easier to understand. So this is our input array, and again, the first thing that we'll do is we'll divide this. Okay, so 9, 8, 3, 7, 5, 6, 4, 1. So we'll divide this into two sub-problems. So this becomes the first sub-problem, 9, 8, 3, and 7. And then 5, 6, 4, and 1. And then what we'll do is we'll divide these sub-problems into smaller sub-problems. So this becomes 9, 8, and 3, 7. So divide it at the half. Okay. Divide it at the half here. So we'll also divide it here to 5, 6, and 4, 1. And then we'll divide this further into half. So 9, 8, and 3, 7, 5, 6, and 4, 1. Now, there are only 1 items per sub-problem this time, so we can't divide it any further. So this time, what we'll do is the merge step na. Okay? So what we did so far was just divide the sub-problems into smaller sub-problems by dividing it into half. Now, the meat of the process of merge sort comes in the merging part. That's why it's called the merge sort. So when we merge, for example, 9 and 8, we have to consider which one is smaller. So when we merge 9 and 8, 8 is smaller, so 8 comes first before 9. Okay, do the same with 3, 7, so 3 comes first before 7. 5 and 6, so we have 5, 6. 4 and 1, so 1 should come first before 4. Okay, then now we'll have to merge these two sub-problems. So 8 versus 3, which one is the smaller? So it would be 3. Now this time we'll have to compare 8 with 7 because 3 is done, right? So 7 versus 8, 7 is smaller, so 7 gets copied first. And then since we don't have anything left here, then we'll just copy 8 and 9 here. Okay, then we'll do the same here. So 1 versus 5, 1 wins. 4 versus 5, 4 wins. 5 and then 6. Okay, and then finally we'll merge these two to solve the original problem. So we have 1 versus 3, we have 1. And then now that 1 is done, we'll move to 4. So 3 versus 4, 3 wins, so 3 is done. And then we'll move to 7. Then 4 versus 7, 4 wins. 5 versus 7, 5 wins. 6 versus 7, 6 wins. And then we'll have 7, 8, and 9 as the last one. So this is now your merged version of the final answer, and this is your sorted version of the original array. So 1, 3, 4, 5, 6, 7, 8, 9. Okay, so that is merge sort. So divide into smaller subproblems until you can't divide it anymore. That means that there's only one item per subproblem. Okay, so you can't divide that further. Then after that, you'll have to merge everything together by comparing which one is the smaller item, and then copy that first to the merged version. Okay, so that is merge sort. Now, for the analysis, the height of the recursion tree is log of n base 2 because you're dividing it by 2 every step of the way. So let's say, for example, earlier in our example, n was equal to 8, right? So if there are 8 here, we'll divide it into 4 and 4. Then 4 becomes 2 and 2. And then this becomes 1 and 1, right? So what is the height of this recursion tree? So the height is 1, 2, 3. Height is equal to 3. And 3 is log of 8 base 2, right? Because 2 cubed is 8, right? So that is the height of our recursion tree. Okay, log of n base 2, because we are basically dividing it every iteration into 2. Okay, and then there's O of n work per level, because basically you're merging everything, so that's per level. You are comparing all items, O of n. So all in all, since there's log n levels, and then there's O of n work per level, that would be n times log of n base 2. So that is O of n log n. Okay, and that is best, average, and worst case. It doesn't matter if it's already sorted, reverse sorted, random order. The running time stays the same because the process remains the same anyway. So even if it's already sorted, like 1, 2, 3, 4, we don't know that it's already sorted, so we'll still divide it the same way as we did, right? And find out only later that it's the same order, right? So we don't know the sortedness of the array, so we'll still proceed as usual. Okay, so the same running time, best, average, and worst case. And then for memory, it will use O of n, because this time we are using extra memory to store the merged version of the array. So if we go back to the the merged pseudocode, we have an extra array here which is named B, which is an empty array of size n. So it's the same size as array A, and we copy contents to B when we merge. That's why we have an extra memory of O of n, the same size as the array. Okay, so that is merge sort. So the good thing about this is that input structure does not affect the running time. Okay, so as I mentioned earlier, whether it's already sorted or reverse sorted or randomized, it will have the same running time. Okay. Okay, next, let's move on to Quicksort. And Quicksort is actually one of the most elegant sorting algorithms. And it's very prevalent in practice. A lot of applications that need sorting actually use Quicksort because it's elegant. And it also uses divide and conquer, just like merge sort. However, there is no merge step. So it only divides and conquers. Okay, no merge. Okay, so how does Quicksort work? So the idea is you partition the array around something called the pivot item. So what is a pivot item? So you'll just pick some element of the array, some item, and you call that the pivot. Okay? And what you'll do is you'll rearrange the array according to the pivot, so that the items less than the pivot should go to the left of the pivot, and items that are greater than the pivot should go to the right. Okay? So let's say we have 38251476 as the array, and let's say that our pivot is 3. So what will happen is so if we use this as the pivot, when we rearrange this one, so 3 will be here, 8 would go to the left, to the right because it's greater than the pivot. 2 would go to the left. 5 would go to the right. 1 would go to the left. 4 would go to the right. 7 and 6. Okay, so this one are less than 3, and then this ones are greater than 3. Okay, so that is what we mean when we partition around the pivot. We rearrange the array according to the pivot item. Okay, so this one, yeah, it's the same thing. So for Quicksort, what we'll do is so we'll partition according to the pivot, and then we'll call Quicksort on the left half of the partition and the right half of the partition. Okay, so basically we'll call Quicksort after partitioning. We'll call Quicksort again on this one and on this one. Okay, but why does it work? Okay, so basically what partitioning does is it puts the pivot into its correct position. So if you go back here, that puts 3 in the correct position, because regardless of what the order here is, we know that 3 is in the correct position because all the items to the left are less, so it could be 1, 2 here. No matter what the position is, this is the correct position for 3, and then all the others here are greater than 3, so whatever their order is here, we know that this is the correct position for 3. Okay, so we are putting the pivot into its correct position, so we are adding or putting an item to its correct position each iteration, and we're recursively solving the sub-problems to take care of themselves. Okay, so by doing Quicksort again on this one, so it will resolve or sort itself, and then so it will also sort itself here. Okay, so now there are 2 ways that we could partition. It could be out of place or in place partition. If it's out of place, you could use extra memory like a deck, a double-ended queue, wherein we just need to iterate through the input array, and if it's if it's greater than the pivot, then we add it to the end because it's should be to the right, and if it's less than the pivot, we add it to the front of the deck. So remember your data structure for the deck, it's a double-ended queue, so you can add to the front or the back, right? So for example, if we have this one, if our pivot is, let's say, 5, so this is our deck currently, 3 is less, so we'll add to the front. 8 is greater, so we'll add to the back. 2 is less, so we'll add to the front. 1 is less, so we'll also add to the front. 4 is also less, we'll also add to the front. 7 is greater, 6 is greater, so we'll add to the back. So now this part is in the correct position already, but we'll have to redo Quicksort on these sub-problems here. Okay, so that's out of place partitioning. And in out of place partitioning, we have running times that could, at the best case, worst case, or average case, runs in O of n. Okay, in average. Okay, because basically you'll have you'll just go through each partitioning naman lang. You just go through each item one by one. So regardless of whether that's sorted already or not sorted, it will happen the same way. Okay, and for the memory, it's O of n because, well, you have the extra memory for the deck. Another way that you could partition is by doing an in-place partitioning. You don't use an extra data structure, but instead you do in-place swapping. So you swap the pivot with the first item of the array, and you iterate through the input array and perform the partition using swaps. So you could do something like this, wherein at the first position you put the pivot here, and then from 2 up to s, something called s as the variable, that's the less than the pivot. Then from s up to u, that's greater than the pivot, and then after u, that would be unpartitioned pa, so it's not yet done. Okay, so you could have like partitioning for in-place partition, like here. So first you'll choose a pivot, and then you put it at the start or the first part of the array, and then what this does basically is just arrange everything in such a way that you will put the partition or the items that are less than the pivot. So it will look something like this. So the pivot would be placed at the first item, less than pivot is 2 to s, and then greater than pivot from s to u, and then u up to the end are the unpartitioned ones. Okay, so this is just what it does basically. So in place partition. Okay, so it's possible to do the partitioning in place, so it's still O of n, but you don't take extra memory. So O of 1 lang ang memory niya. Okay, now how do you choose the pivot? Because it turns out that choosing the pivot is important for the performance of Quicksort, because if you choose a good pivot, then it will have a good running time. Otherwise, if it's a bad pivot, it would be also have bad running time. So the running time depends on the quality of the pivot. Okay, so let's see how it affects the running time. So let's say if we always choose the first element of the array as the pivot, what is the estimated running time of Quicksort if the input is already sorted? Okay, so what does that mean? Let's say that the input is already sorted. 1, 2, 3, 4, 5. And let's say that we always choose the first element as the pivot. So if we choose this as the pivot, will that actually help us in the division? Well, it won't, because what this does is it leaves nothing to the left and everything to the right. Okay, so if we do the same for this subproblem and choose this as the pivot again, there's nothing left on the left and everything is on the right. Okay, so you're not actually dividing the subproblem, you're only reducing it by 1. Okay, so it's actually sum of arithmetic series, so that would be O of n squared if that happens. So that would be a bad running time. So it's just similar to insertion sort and selection sort. Now, how about if we somehow always select the median element of the array as the pivot? And remember, the median is the 50th percentile, so half of the elements are smaller, half of the elements are bigger than that element. What if we always select magically the median element as the pivot? Then it would run in O of n log n. Why is that? Because it would be similar to merge sort, that you're dividing it into half, right? Because if it's always, let's say, the median, so even if it's like not sorted, so let's say 4, 3, 7, 8, 1, 6, 5, 2. Yeah. So if that's the case, the median of this one, let's add 9 to make it easier. The median of this one would be 5, right? So 5 is the median. So if you partition this one, 9 would be here, 2 would be here, 4 would be here, 3, 7, 8, 1, and then 6. Right? So you perfectly divided the array. There's 4 to the left and 4 to the right. Okay, so you divided it in half, and then after this one, if it's the median again, it will be divided into twos also, right? So that would be just like merge sort, right? Ang behavior niya. So that's O of n log n, and the height of the recursion tree is also log of n, and partitioning takes O of n, right? But that is if we always choose the median, but we can't always choose the median because we don't know what the median is. So our goal, therefore, is to choose the pivot that makes two nearly balanced partitions. We don't want an imbalanced partition because that would not actually help us, right? So an imbalanced partition would be something like, if you partition it and it looks something like this. So this is the pivot, and then it's only small here, and then there's a big sub problem in the right half, or the opposite. So pwede man na big sa left half and like small or not, almost nothing in the right half. Okay, so we want to make it balanced, na even if it's not perfectly half, at least hindi siya imbalanced. Okay, so to do this, we'll actually use random pivots. Okay, we'll choose randomly from the items, and if we choose the pivot randomly, each item has an equal chance to be chosen, and the random pivot is pretty good often enough. Okay, because you don't really need like a 50-50 split. Getting around 25 to 75 split is usually good enough. Okay, so even if it's around this range, like 25 tapos 75, although it seems fairly imbalanced, but usually good enough running time na siya. Okay, as long as hindi siya like something like 10 to 90, that's very imbalanced, right? So getting 25 to 75 split is usually good enough, and half of the array elements give a 25-75 split or better if used as a pivot. So if it's a 50-50 chance, then just choose randomly, because you have a 50-50 chance of getting a good pivot or not. Okay, so that is how we'll choose our pivot in Quicksort. So again, the running time depends on the quality of the pivots. Best case, average case is O of n log n if you use random pivots, and at the worst case, it's n squared. That is if we choose like a pivot that makes it super imbalanced. Okay, and again, the memory is O of 1 if we use in place partition. Okay, now let's go to the next sorting algorithm, which is heap sort. Now for heap sort, this is an efficient sorting algorithm that uses the heap data structure, and it's an example of an algorithm where the right data structure actually improves performance. So the heap data structure is like a tree-like structure. Okay, so it's an array object that can be viewed as a nearly complete binary tree. So if you remember your binary trees, those are trees that have at most 2 children. Okay, and for the heap, the tree is completely filled on all levels except for the last. Okay, so that, and then in the last level, it's filled from left to right. So the root is usually at the first element of the array, and if you want to get the parent of the parent index of that item, then you just get the I over 2. If it's the left child, make it 2 times the index. If it's the right child, 2 times the index, then plus 1. So putting all of that together, so this one would be the root because it's at index 1, 16. And then if it's the left child, so times 2, so it's at index 2 basically. So this is the left child, ang 14, and then the right child is at 2 plus 1, which is at 3. Now, so 14, ang children niya would be 2 times 2 is at 4, so that's 8, and then 7. And then for 10, the left child is at index 3 times 2, so that's 6, so it's 9 and 3 here. Okay, so that would be how the heap is displayed in the array. Okay, so if it's something like this, basically ang itsura niya would be something like this: 16, 14, 10. Okay, so since 16 is at index 1, because this is the root, right? This is the root. So ang left child niya would be at 1 times 2, because left child is index times 2. Ang right child is at index times 2 plus 1. So 14 would be there, and then 2 plus 1, 10 would be there. So that's why it's at index 2 and 3, kasi 14 and 10. Okay, so that's the heap data structure. So that is how this looks like in actuality. So 16, 14, and 10. Si 14, si 8 and si 7 ang children niya. That's 8 and 7. Si 10, si 9 and 3 ang iya children. And then for 8, the children are 2 and 4. And for 7, for 7, si 1 lang ang children niya. Okay? Now, for the height of the heap, so if the heap has n elements, the height of the heap would be log of n base 2, because we're basically dividing it into 2 also per element. So let's say, for example, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 10 log of 10 base 2 would be 2 point something, and if we get the ceiling of that, that's around 3. Okay, so sorry. So again, log of 10 base 2 is actually around 3 point something, right? Because log of 8 base 2 is already 3. Log of 16 base 2 is 4. So log of 10 base 2 should be around between 3 and 4. So if we take the ceiling of this, we should have 4 levels. So 1, 2, 3, 4 levels. That's the height of the heap. Okay, now there's something called the max heap and the min heap. So a max heap is where the in all nodes of the heap, the parents are have a bigger value than the children. So you can assume that the largest is at the root. Sa mean heap naman, it's the opposite. The parents are always lesser than the children, and the smallest one is at the root. Okay? So for heap sort, what we'll use is the max heap. So the largest item should be at the root, and we need to maintain two properties for the max heaps during execution, which is the shape and the heap property. So for the shape property, the leaf at the depth k greater than 0 can only exist if all 2k minus 1 nodes at depth k minus 1 exist. Okay, basically what this means is you cannot fail the next level if you haven't failed up the previous level. Okay, you cannot do something like this. So if you have already failed this level, if you want to finish this level, you have to fill this in first. You can't skip here if there are still empty pieces here. So you can only do that if this has been filled and this one is not also possible. You can't add this yet until you've filled up the previous level. Okay, and if there's an extra level that hasn't been completely filled, that's fine, as long as you do it from left to right. Okay, so this is only fine because it's only the last level, so you still have space left here. That's fine, but you can't do something like this wherein it's starting here already when there's still space here. Okay, so you can't do that. So it must be filled from left to right. Okay, and then for the heap property, then we'll maintain the max heap property that if the node has any child, the value should be greater than all of its children. So meaning the parent has to be bigger than its children. Okay, so we'll do something called max heapify, which maintains the heap property. So given an array A and some index I, we'll turn it into a heap basically. So we'll assume that the left and right subtrees of I are already max heaps, and before that, A sub I may be smaller than its children, so we should try to check if it follows the heap property, and if it does not, then we should swap them. And then after doing max heapify, we are now sure that the subtree rooted at I is a max heap. Okay, so basically what you'll do is you'll just compare the three items, basically something like this. So this is the root, this is the left child, we'll just call this the parent, the P, the left child, and the right child. So we'll just compare the three. Is the left greater than this one, or right greater than this one? If it does, then we'll swap out whichever is bigger than the two to the parent, and then while we do that, we'll need to max heapify that part again. So again, compare the three. Okay, if necessary, swap A sub I with maximum of the children, and if we swap, we need to max heapify again. Now, why do we need to max heapify again? Because we assume that the subtree rooted at the children are already max heaps. So let's say that it's something like this. So let's say this is 15, 14, 2, 9, and then 3 and 7. And let's say, so these two are already max heaps, right? So 15, 3 and 7, 15 is the max, 14, 2, 9, 14 is the max. But how about if we put a 5 here? So if we put a 5 here, we need to check between these three, right? So among the three, which one is the biggest? It's actually 15. So we need to swap 5 and 15 here, so that 15 will be here, and what should be here is 5. But if we stop here, this is not a max heap anymore, because this sub 3 does not follow max heap, because 5 is not the biggest among the 3. So if we swap something here, then we need to max heapify again, starting from that node, because it could have violated the previously assumed assumption that there is a max heap at that sub 3. So we max heap again here, so 7 will be moved here, and then 5 will be moved down, and then after that, then it's already a max heap again. Okay, so swapping values may violate max heap property, that's why we need to do it again. Okay, so continue swapping down the heap until sub 3 rooted at I is a max heap, and if it's a leaf node, then it's obviously a max heap already by itself, because there are no children. Okay, so let's see an example of this one, of max heapify. So we have 16, 4, 10, 7, 4, 10, 14 pa. 16, 4, 10, 14, 7, 9, 3, 2, 8, and then 1. Okay, so at index 2, so this is index 1, index 1, index 2, so we'll call it here. Okay, so 4, 14, and 7, which one is the biggest among the three? That would be 14. So 14 should be here, and 4 should be swapped here, right? So 4 na lang na siya. But then since we swapped it here, we have to call max heapify here again. So among the three, 4, 2, and 8, which one is the biggest? It's 8. So 8 should be here, and 4 should be here. So this time, since the swap happened here and it's already a leaf, then we can stop. And this one is actually a max heap already, right? Because let's say 16 is the biggest between 14 and 10, and then 14, 8, 7 is the biggest, 10, 9, 3, this one is the biggest, 8, 2, 4, it's also the biggest, and 7, 1, 7 is the biggest. Okay, so this is already a max heap. Now, for max heapify, the worst case is log n, because we're doing at maximum, we could traverse from that root all the way to the leaf, so that is log n height. So that's the worst case. Okay, and the memory is only O of 1 because we're doing it in place anyway. Now, we'll use max heapify in the build max heap. So we'll do the unordered array as the input, and the output is the heapified array. So what we'll do is we'll just call max heapify from n over 2 down to 1. Okay, so we'll just repeatedly call that from a half of the array down to 1. So if this is the example, so this is index 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we'll start at index 5 down to 1. So from here all the way to here. So let's try to build that max heap. 4, 1, 3, 2, 16, 9, 10, 14, 8, and then 7. So we'll start at 16, which is index 5. So 16 and 7, it's already max heap, right? So this one is done. So 2. Okay, at this one, 2, 14, and 8, well, this is not in max heap, so we'll actually swap out 14 and 2, because 14 is the biggest among the 3, right? So 14 would be here, and then 2 would be here. Now, we swapped here, but since it's a leaf, that's already fine. Okay, so the fourth one is done. We'll go to the third one. So at 3, 9, and 10, this is not max heap, so we'll exchange this with 10, right? Because it's the biggest among the 3. So that would be 10 here and 3 here. So now we swapped it here, but since 3 is a leaf, there's no problem. And then at index 2, at 1. So 1, 14, and 16. So we've seen this earlier. It should be 16 here, right? And we'll swap 1 here. But since 1 has been swapped, we need to max heapify again on this one. So 1 and 7 has to be swapped. So this will be 7, and then this one would be 1. Okay, and then finally it would be at 4. So max heapify here. So 4, 16, 10. So the winner would be 16, right? So we need to swap 16 and 4. So this would be 16. This would be 4. But it's not the biggest here, so we'll max heapify again. So 14, 4, and 7. So 4 would be here. But this one will have to be max heapified again. It will be switched with 8. And this one will have 4. Okay, and so now, since we're done from 5 down to 1, we have actually max heapified everything. So you notice 16, 14, 10, 8, 7, 2, 4, 1, 9, 3. Okay, so that is the how to build the max heap. Now, why did we only iterate from n over 2 to 1? Why did we not do it from n down to 1? That is because the other half would be checked using the parents anyway. So there's no need to start from n over 2. So like for example, in let's go back to example of the max heap. Like here, for example, we only started at index 1, 2, 3, 4, 5. So we started here because, let's say, this one will be checked by, so we check this 5 ones in squares, right? Because this one will be checked from here, this one will be checked from here, this one will be checked from here, and this 2 will be checked from here anyway. So if there is something that needs to be max heapified, they will be checked by their parents. So we don't need to go from n down to 1. We can just start from n over 2, which is where the parents would start. Okay, so that's it. And then where are we now? Okay, so if there's n over 2 iterations and log n for max heapify, then the worst case running time is n log n also. Okay, so for the heap sort, what we'll do is we'll build the heap first, and then we'll iterate through the heap to extract the max element, which is the root. So we know that the biggest element is at the root. We'll swap that out with the last element, and then max heapify the remaining items, and then repeatedly do that until you get the sorted version. Okay, so per iteration, the max element is stored at A1, which is the root. So you exchange that with A sub n, which is the last. So you put it at the last because it's the biggest element. Okay, and then you proceed with the 1 up to n minus 1. So you're making it smaller and smaller each time. Okay, so all in all, this is the heap sort algorithm. So build the max heap for the array, then from n down to 1, swap the root with the last, and then max heapify the rest, and then repeat it again. Okay, so let me show you one last example for heap sort. So let's start with already a max heap already. So 16, 14, 10, 8, 7, 9, 3, 2, 4, and then 1. So this is already a max heap. So we're done with building the max heap. So from n down to 1, so we'll start with the last one. So we'll swap that with the first. So 16 and 1 will be swapped. So this one is done already. 16 is the last. So this one is 1. But since we swapped it, we should max heapify it. So 1, 14, and 10. 14 should be here. And then this should be 1. But then 1, 8, and 7. 8 should be here. And then here should be 1. But then 1, 2, and this is 4. Right? So 4 should be here. And this one should be 1. Okay, so let me clean that up. This one should be 4. Then that one should be 1. Right? So we are now done with the first iteration. For the second, we'll swap 14 with the last element, which is 1 here. So 14 will be swapped out here because that's the max currently. And then 1 will be down here, up here at the root. And then we'll max heapify again. So 1, 8, and 10. So 10 will move up. 1 will move down here. And then 1, 9, and 3. 9 will win out. And then 1 will be here. Right? Okay. Next, we'll swap 10 and 2. So 2 will be here. 10 will be here, and that's done. And then we'll max heapify this one again. So 2, 8, 9. 9 is the winner. So 2 will be swapped here. And then 2, 3, 1. Okay, let me make this pretty. This one is 9, right? And previously there was 2 here, but since 3 will win out, 3 will be swapped up here, and 2 would be here. Okay. After that, 9 would be swapped with 2. 9 is done. And then this one will have 2 here. But then it will be swapped out with 8, because 8 is the biggest one out of the 3. And then this one will become 2. 2, 4, 7. So 7 will win out. 7, and then 2 here. Right? The next, 8 and 1 will be swapped out. So 8 is done. 1 here. Then max CP5 again. So 7 will win out. This one will have 1. But then the winner of this would be 4, right? So 4 will be here. 1 will be here. The next will exchange 7 and 2 here. So 2 will be placed here. 7 will be here. That's done. And then 2, 4, 3. So 4 will win out. And then 2 will be placed here. Gamay na lang. So exchange 1 with 4. So 4 will be here, 1 will be here. This one is done. And then 3 will be here. And then 1. Okay. And then after that, we'll go back to swapping 1 with 3 because it's the biggest. So 3 is done. 1, and then swap 2 with 1 here because it's the biggest one also. And then finally we'll swap 2 with 1 back again, so that 2 is the done now, and then 1. And since 1 is the only one left, it's done. So we now have 1, 2, 3, 4, 7, 8, 9, 10, 14, 16. And that's the sorted version using Heap Sort. Okay? So that's it for heap sort. So basically just build the max heap first and then extract the root, swap it with the last, and then max heapify everything again and repeat until everything is extracted. Okay, so it has the same running time whether it's already sorted, reverse sorted, or randomized. So it's still n log n and has memory of O of 1 because it doesn't use extra memory. Okay, so the heap itself is the input array. You just rearrange the items there. Okay, so now you'll notice that heap sort and merge sort have similar running times, but they're both n log n. But the difference is that merge sort is a stable sorting algorithm, meaning it will, if there are ties, it will follow the same order as the input order. But heap sort is not stable because of the heapify property. You cannot assume that the input order is the same as the output order if they are tied. Okay, so that is heap sort. Okay, we are now down to our last, I think, 3 sorting algorithms. So we're almost there. Okay, so next we have for our last 3, these are non-comparison sorting algorithms, and they all run in O of n. Okay, so linear time sorting algorithms, and they don't even compare, unlike our previous 7 algorithms wherein we need to compare either adjacent items or compare it with a pivot or compare like the left and the right when merging. Okay, so the next 3 sorting algorithms are non-comparison sorting algorithms, but they also have restrictions as to when you can apply them or when you can use them. Okay, so for counting sort, the assumption is that each item is an integer in the range 0 to k for some number k. Okay, so you can only use this in limited situations, especially if the range is small, because if it's a big range, like say if it's 0 to 9 ang numbers na assumed mo na there in the input array, then that's fine because 0 to 9 it's a small range. But if the range of numbers in your input could be from 0 to a million, then counting sort is not a efficient algorithm to use. Okay, so it's not good for sparse arrays wherein you could have input numbers like 1000 and then the next one is 5000 and then the next one is a million already. So it's not compact, but it's sparse. Okay, so what do we do for counting sort? So because we know that the items are in the range 0 to k, what we'll do is we'll just basically count how many numbers are there for each number from 0 to k. Okay, for x from 0 to k, we'll count the number of that number in the array, and then what we'll do is whatever is the count of that number, we'll add however many that count is to the output array. Okay, if that sounds ridiculous or it sounds complicated, it's really not. Okay, so I'll show you an example in a while, but basically for the analysis of this one, we'll notice that for the first loop, this is O of n. Why is that? Because we're totaling the counts, right? So we can basically just go through the items in the array one time, so from 1 to n, and then we can update the counts of each number in A. So let's say if the range is from 0 to 5, 2, 3, 4, 5, and our input array was 1, 2, 1, 3, 0, 5. So if we see 3, we tally 1. See 1, tally 1. 2, 1, 0, 5. So our final tallies are 1, 2, 1, 1, 0, and 1. So you can just go through the arrays input array one time So it's only n iterations. Okay, and then for the second one, it's also n iterations because we're basically just recreating the array anyway. So the total of the counts is n, right? Because that's 2, 3, 4, 5, 6. So there are 6 items in the array, and this is 6 ang total niya. Okay, so how does this work exactly? Okay, so if we have this one, basically what we'll do is we'll just count. So we're assuming this is from 0 to 5. So how many zeros are there? There are, so 0, 1, 2, 3, 4, 5. So this is the count. For 0, there's none. For 1, there are 3. For 2, there are 2. For 3, there's only 1. For 4, there's 2. And for 5, there's only 1. So what will we do with these counts? So basically, to recreate the sorted version, we will just, well, for 0, there's none, so we won't add any zeros. For 1, there's 3, so we'll just add 3 ones. Then for 2, 2 twos, 1 3, 2 fours, and 1 5. And that's it. So this is already the sorted version of the input. And that is by counting the number of occurrences of each number from 0 up to k. Again, this is assuming that we know the range beforehand. Okay, so it's that simple. Just count the number of occurrences, and then however many that count is, that's the number of replications for each number you'll put in the sorted version. Okay, so that's counting sort. So it's a linear time sorting algorithm. Best case, average case, worst case is O of n, and the memory is O of k because we are keeping the counts, right? So that's an extra array allocation for the counts. Okay, so that's counting sort. Next, let's look at Radix Sort. So sa Radix Sort naman, this is also non-comparison, but this is a digit by digit sort. Okay, so what we'll do is we'll sort. So this is applicable for numbers, but you can also apply it to tuples or other things that require multiple fields. But basically, what we'll do is we'll sort on the least significant digit using a stable sorting algorithm. So it could be something like merge sort or counting sort even. And then we'll do this for the second least significant digit and so on until we reach the most significant digit. Then after that, we've already sorted everything. So how does that work exactly? Okay, so let's see. So let's sort through the least significant digit, which is the ones digit. So if we use this as the basis, the first one should be 720 because it has 0, right? 720. After that, it should be 5, right? So 355. And then 6. So 4, 3, 6. And then we have a tie at the 7s. But since it's a stable sorting algorithm, so it should be the same order as the input if there are ties. So 4, 5, 7 and 6, 5, 7. They're done. And then there's a tie at 9 also, but again stable, so it should be 3, 2, 9 and 8, 3, 9. So we have sorted by the ones. So sorted na siya by the ones. Next, we will sort to the tens using the tens. So sa tens, the first one should be 2, right? So since there's a tie for 720 and 329, we'll use the same order because it's stable. 720, 329. After that would be 3s, right? 436 and 839. Okay, after that would be all 5s. So 355, 457 and 657. So again, because it's a stable sorting algorithm, we should follow the original order if there are ties. So sa 355, 457, 657, it's the same order. And then finally, we'll sort to the most significant digit, which is the hundreds in this case. So in that case, the first one would be 3, right? So there are 2 3s, so we'll follow the original order, 3 to 9 and 355. And this is important because we have assumed that the previous place has already been sorted. So if there are ties, then we are assured that the 2 here is less than the 5. Okay, that's why we need to follow their original order also. Okay, and then sa next we have 4, 436, and 457, and then the next we have the 6, which is 657, and then 7, 720, and last 839. So you have now sorted everything in the correct order. So 329, 355, 436, 457, 657, 720, 839. Okay, so that is Radix sort. So you sort through the least significant digit first, arrange them according to this one, and then the next one, and then the next one, using stable sorting. Okay, so that's Radix sort. So you could even use counting sort as the auxiliary sorting algorithm, because we know that the range is only from 0 to 9, and it's also stable, right? So let's say that D is the number of digits, so that would be D times O of n, because counting sort runs in O of n. So if it's D times O of n and if D is constant, then it's still about O of n. So it's still a linear time sorting algorithm. Okay, that's Radix sort. Worst case, best case, average case, the same, O of n, and then there's also memory of O of n, because if you are sorting it per what do you call this, per significant digit, then you'll have to transfer it into another array. Okay, so there's an extra memory for that one. Okay, lastly, we'll look at something called the bucket sort. For the bucket sort, what we'll do is it's a distribution sort, and it distributes items into n buckets. Okay, so if the items are uniformly distributed, then the bucket should not contain too many items, and what we'll do is we'll sort each bucket and combine the answers. Okay, so this will be better shown with an example. So let's say that the range of items are from 0 to 100, and so we'll use the tens as the buckets. Okay, so for 78, that would be in the sevens. For 17, that would be here. For 39, it would be here. For 26, it would be here. For 72, that would be here. For 94, it would be here. For 21, it would be here. For 12, here. For 23, here. And 69, here. So you'll notice that some buckets contain multiple items and some buckets contain nothing, and that's fine, okay, because not everything has to be in one place. So what we'll do is we'll sort each bucket. So for 0, there's nothing. So for 1, that would be 12 and 17, and then for this one, that would be 21, 23, 26, and for this one is 39 only, 69 only, 72, 78, and then 94. Now, you might say, aren't we doing too much because we're sorting a lot of things? But, well, not really, because if you have distributed the items in such a way that it was fairly distributed or uniformly distributed, then each bucket should contain only a few items. So here, you're only sorting 2 items or 3 items, and that's fine. That's very manageable. Okay, so after doing all of that, then we'll combine all the answers, so starting from 0 all the way up to 9. So we'll have the final answer of 12, 17, 21, 23, 26, 39, 69, 72, 78, and 94. Okay, so just combine all the items from starting from 0 and then all the way down to 9. Okay, so that is bucket sort. Distribute the items into buckets, sort each bucket separately, and then combine the answers. Okay, so it's also a linear time sorting algorithm. The average case is around theta of n if it's a uniform distribution. Worst case is if it's badly distributed, like you're putting everything into one bucket. So that would be O of n squared, because we could do maybe insertion sort because you assume that it's uniformly distributed, but in fact it's really not. So yeah, it's O of n squared here. And then the memory, of course, is O of n because you're using extra buckets for the sorting, right? So that's extra memory as well. Okay, so that's it. That's all of the sorting algorithms that we'll discuss. So to review, we discussed selection sort, which is basically the idea is to select the first smallest element and put it in the first item, pick the second smallest element, put it in the second item, and so on. So it's very naive, right? It runs in O of n squared. Insertion sort naman is when you try to insert the items into the correct position, just like when you're sorting a hand of cards. Okay. For bubble sort, what we'll do is you'll look at adjacent items and swap them if they're out of order, and while you're doing swaps, repeat the process. So starting from the last, look at adjacent pairs. If they're out of order, swap, 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 and yeah, so do that repeatedly until there are no more swaps left. And then for shell sort, this is when we divide it into 2D arrays using gaps. So we'll arrange it into 2D arrays and then sort per column, and then we'll make the gap smaller until it reaches 1, which increases the sortedness of the array at each iteration, and you're moving out of place items more faster, right? And then there's merge sort, which uses the divide and conquer approach. So you divide the sub problems into half until you cannot divide it anymore when it's only individual. And then the meat of the sorting algorithm is when you merge. Okay, so when you combine everything, you compare the left and the right, or whichever should come first should go down, and then proceed to the next item. So left, right, whichever is smaller gets merged first. And then there's Quicksort, which is a very elegant solution. Uses divide and conquer as well, and then uses the pivot to partition the array, and then you put items less than the pivot to the left, items greater than the pivot to the right, and then do it recursively to the left and the right sub-problems. Then for heap sort, this is using the heap data structure, which is max heap basically. So the max heap is when you have the parent having a bigger value than both children, so the biggest item is at the root actually, right? And so you use that max heap, and then you extract the biggest item, you put it at the last, and then you max heapify again, and then repeat it n times. And then counting sort assumes that you have items ranging only from 0 to k for some value k, and then you just count how many times does 0 come in the input, how many times does 1 appear, how many times does 2, and then you just replicate it depending on the number of counts. Okay. And for Radix sort, this is when you sort by ones first, sort by tens, sort by hundreds, by thousands, and this also increases the sortedness of each one by using a stable auxiliary sorting algorithm. And then finally, bucket sort is when you you distribute the items into buckets, and if it's uniformly distributed, then you would have divided up the items pretty evenly, and then that's when you sort each bucket separately and then combine everything. Okay, so that's everything for sorting algorithms. We'll stop here for now, and I will see you in the next video.